Our final speaker for the morning before the panel is Xiao Liu from Princeton and NOAA GFDL.
All right. Okay. Go backward. Okay. Thank you. I would like to thank the organizer for putting this really nice session together and for inviting me. It's a pleasure to be talking about here some work I've been doing as a postdoc at NOAA GFDL, simulating anthropogenic perturbation of nitrogen cycling and transport across the land-ocean continuum. And today I'll be focused on talking about, from a global perspective, the roles of rivers, and I'll try to make the linkage between the long-term changes in river nitrogen loading and the coastal ecosystem responses. So before I get started, I want to thank my collaborators from both the land and ocean modeling group at NOAA GFDL, and my postdoc funding source from the Cooperative Institute of Modeling Earth System, which is a joint effort between Princeton and NOAA, and of course thank OCB funds for bringing me here. Okay. So we've learned a lot from a number of talks yesterday about the challenges being faced by our coastal and estuarine environment and due to anthropogenic change. So just very briefly, we see harmful algal blooms and toxins that they produce, associated hypoxia and dead zone, and even some decline of the submerged aquatic plants due to surface shading of the plankton. Phytoplankton in the surface. All of those pose a threat to our coastal ecosystems and the service they provide. These coastal problems are in large due to eutrophication, and the rivers are known to be playing a major role, transporting a lot of nitrogen and as well as other nutrients and material to the coastal ocean. And since this problem started in the late 70s in the United States and later around the world, many efforts have been made trying to address this problem. What's the impact of river nitrogen loading on the coastal ecosystems? But still, today, many of the fundamental questions, including mechanism, remain not fully understood, and especially those related to the transport and exchanges problem, because those are the quantities very difficult to measure. So some of the questions I'm particularly interested are, to the first order, how is this river nitrogen processed and cycled while it's being transported across the land-ocean interface? And how much is removed on global scale and by what processes? And also how much nitrogen is ultimately transported to the open ocean, and where does it end in the open ocean? And second, maybe more importantly, how is this increasing river nitrogen loading changing our coastal nitrogen cycle and changing coastal ecosystems? And how is this impact different from coast to coast, system to system? Okay, so in order to resolve these problems, we really need to track the nitrogen down across this land to ocean continuum, aquatic continuum, and really need to dig into each of the boxes and see what's going on there. And also for a global scale understanding, we need a consistent framework that are allowing us to do a systematic evaluation and a comparison. So bear with me, we will have to start from the land. Okay, so the ultimate source of anthropogenic nitrogen comes from the land, because this is where we live and make an impact. So what I'm showing here is the schematic of the terrestrial and aquatic nitrogen cycling model represented in the NOAA GFDL's land model LM310. Basically, in the pre-industrial period, when human impact was really minimal, the majority of the source on land of nitrogen is by nitrogen fixation. This is by the natural land plants. Nitrogen fixation is not only occurring in the marine environment, but also a major source of nitrogen on land. And we see like more than 80% of the nitrogen source on land comes from the natural into fixation. And then we also see a little bit of anthropogenic, the atmospheric deposition. Some of the natural phenomena such as lightning will also contribute to the nitrogen source. However, by the beginning of this century, this total nitrogen source on land have tripled. And we see now with a large contribution from fertilizers, we also see increasing amount of nitrogen fixation by agricultural plants such as the beans. And also increasing amount of deposition from the atmosphere due to fossil fuel combustion. So the model takes in all those nitrogen sources on land and processes and simulates the nitrogen cycle through the terrestrial and soil and aquatic system, and yields as an output the river discharges, both freshwater as well as nitrogen loading. This is both the dissolved organic and inorganic nitrogen. So the long-term simulation by this model suggests that the total nitrogen loading from the river to the coastal ocean increased from 28 to 49 teragram nitrogen per year. So on global scale, this is almost doubled. So where do we see the hot spots of river nitrogen loading to the coastal ocean? What I'm plotting here from the land model output, this is the largest 150 rivers out of the over 2,000 rivers simulated in the model and ranked by total nitrogen loading. And you can see the pie size, the circle size is scaled by the total river loading, and the color indicates the long-term significant trends over the past 50 years. And you can see many of the rivers here, including the major rivers in the United States, have experienced an increase, significant increase in river total nitrogen loading to the coastal ocean, somewhere between 10 to 35% over 15-year period. So that's a lot of change. And I want to point out here, the loading is a function of both freshwater discharge as well as the concentration in the waters. So some of the blue dots you see here, you might be wondering what happened there. So this is more due to the freshwater, the hydrological cycle changes and river drying out rather than the decreased concentration in that waters. Okay, so this amount of nitrogen, a huge amount of nitrogen added to the coastal ocean will be transformed by a very complex biogeochemical process in coastal waters. So I'm showing a schematic of the some of the key processes involved in coastal nitrogen cycle represented in our ocean biogeochemical model, COBAL. So COBAL is a fairly sophisticated framework including 33 tracers, and also part of the GFDL's or system modeling contributing to the CMIP6 effort. So we can see in the coastal waters, the nitrogen comes in externally from river flux, a major contributor, and also comes from the atmospheric deposition, and also by nitrogen fixation by the isotroph in coastal water. And this inorganic matter will be transformed to organic matter, and a particle will be sinking to the bottom. And a large percent of the sinking particle will be remineralized and returned back to the water column. And there will be some percent get buried in the sediments, which is permanent removal from the system we consider. And then in some of the oxygen depleted waters, denitrification may also occur, returning the nitrogen back to the atmosphere. Okay, and of course, the coastal waters also experience very dynamic exchanges with the open ocean, but the sign of the net transport between the coast and open ocean will be depending on different systems. Okay, so this is what we have in our model, capturing the key processes. And we also, of course, calibrated the model for the better capturing the coastal processes. But one of the bigger challenges for using global model to simulate coastal processes is the coarse resolution, often insufficient to resolve the complex hydrodynamics and the geometry. So the question is is our ocean model good enough to capturing the coastal ocean exchanges, and what resolution do we need in order to do so? So those are the very important questions to answer before we can proceed. All right, so we did our test. So one commonly interested matrix to understand the lateral transport is the coastal retention time scale, or we would like to call it a residence time. So at coast resolution, the problem of the inability for the model to resolve the coastal bathymetry and eddies and everything often results in an under retention of waters. So the water doesn't really stay on the shelf that long at coast resolutions. So what I'm going to show you here is a simulation animation of a suite of the simulation with a dye release experiment. So we did it within our ocean model at different resolution from 1 degree, half, a quarter, and 1/8 degree. At 1/8 degree is very high for global model. Okay, so basically we release dye everywhere in the global coastal ocean, shallower than 200 meter, and we let the dye go. So I'm just showing the North American part of the global picture. So hope you can see the dynamics on the shelf here. If you like, you can pay attention to somewhere near the Mid-Atlantic Bight, or you can pay attention to here. The shelf west of Florida will be repeating after a year if you want to see it again. So basically what we see here is at coarse resolution, the dye quickly dilutes on time scales of within 2 or 3 weeks. Well, at high resolution, the dye stays on the shelf much longer for several months. So it really tells us that resolution matters to capturing this coastal ocean exchanges. All right, so we follow up on this, and we designed and implemented a coastal age tracer that allow us to calculate coastal residence time globally. So basically the domain, we're interested in the coastal component of the 66 large marine ecosystem globally. And what I'm showing here is the coastal residence time average for each of the system we consider. And you can probably see it. So the residence time range between 1 week from the very narrow shelf and boundary currents to a couple of years on the high latitude wider shelf and some of the semi-enclosed systems. And then we compare this with some observations. We compile a list of observations based on geochemical tracer estimates. And I don't want to see all the details, but the conclusion here is at a quarter degree and at the 8th degree, the observation and model estimate of the residence time match well with each other. But at lower resolution, we tend to underestimate with the model. So it gives us a confidence of using the quarter degree model to address the question that we're interested here. Okay, so we force the model, the coupled ocean biogeochemical model by the GRA reanalysis winds and atmospheric condition. And we give the model monthly varying river nitrogen loading and freshwater discharge from our land model simulation. And just in order to tease apart the river impact, we give a constant atmospheric input of nitrogen, and then we spin it up for 184 years, and then we run 50 years for the past 5 decades for analysis. So this is just part of the validation process showing the nitrogen concentration between model and observations. We see a fairly good correlation here. Okay, so now I'm going to show you the results. So this is the mean nitrogen budget, global coastal nitrogen budget average for over the 50-year period. So this is the, not working. Okay, in the middle, that's the coastal domain with the open ocean boundary on the right side. Any number in red, that's the source, and blue is in the sinks. So overall, we can see river contributes a lot, about 45 teragram nitrogen to the global coastal ocean. with both DIN and the TON. And on the right side, we can see oceanic influx also contributes a lot of dissolving organic nitrogen, about the same magnitude. And this nitrogen, inorganic nitrogen comes in, and will be converted to organic matter, and a large amount of organic matter actually transported back to the, it's not working, but back to the open ocean as the TON. And there's a small amount of burial, not small amount, about 11% burial, and denitrification also contributes a lot of nitrogen loss. So here, basically showing the same thing, but with the time dimension. So we can see the historical changes in nitrogen sinks and source. So the point I want to make here, you can see on the left, that's the river input, the 2 on the bottom. The contribution of river input really increases over year from about 36% to 48% to the, that's the contribution to the total coastal nitrogen source. On the right side, we can see increases in all 3 sinks terms, but the relative contribution hasn't been changing that much. So the question here is the increasing amount of source from the river being balanced by the increasing sink terms? Okay. So now we need to go back to this slide. One term I didn't mention is this coastal nitrogen inventory change, because when we talk about budget terms, often we assume it's imbalance and there's no net changes in the inventory. But here you will see there's a small positive change. I say it's small because compared to other fluxes, it's really small. But I want to mention this is unit nitrogen per year. So every year you have that amount of nitrogen added to the coastal ocean, and over long term, it really adds up. So how has that been changing? The coastal inventory nitrogen has been changing over the years. Okay, so what I'm plotting here on the top, on the left, that's the total nitrogen in global coastal waters. And this has a magnitude about 340 teragram nitrogen. I show 2 simulations. The red one is the baseline simulation with both dynamic physics and dynamic river forcing. But the black line is we replace the river forcing with the climatology forcing. So that's really only reflects the dynamic physics. So you can clearly see if you're just running with the physics, there's no clear trend, but you can see there's a very clear increasing trend with the red simulation, with the river forcing. And by subtracting the 2, we can see we get very clear signal due to the river impact. So this is the changes, accumulation of nitrogen in coastal waters. And on the bottom, I'm just trying to show you a global map. I'm doing the same analysis for different coastal systems. And you can see many of the systems are experiencing rapid increase in total nitrogen inventory, especially as Baltic Sea and Yellow Sea and North Sea. Okay, so what about biogeochemical responses? We've seen eutrophication, but is there impact on ecosystem responses? So here I'm basically showing a very similar analysis. This is net primary production. Interestingly, we can see for both simulation on the left, there's an increasing trend, but with the river forcing, the trend is much, the signal is much stronger. And here we can see that on the bottom, besides the system I was just talking about, Southeast Asia and the Arabian Sea really stands out. So those are the systems very sensitive to the primary production change, very sensitive to changes in the river loading. And similarly, this is the benthic flux minus burial. I'm doing this because that sort of represents the amount of nitrogen, organic nitrogen need to be respired at the bottom. This is very important in terms of considering coastal hypoxia. And we see a similar pattern of increasing oxygen demand in about half of the global systems. All right, so now we've seen accumulation of nitrogen in coastal water. We've seen biogeochemical responses in terms of primary production and oxygen demand, but can we really have a quantitative understanding of what drives the sensitivity? And how do we really link the biogeochemical responses back to the changes in river loading, and can we try to understand the mechanism? Okay, so what I'm plotting here, each dot represents one coastal system, and here is that. Okay, I'm plotting the changes of river nitrogen loading as a flux, influx, over the 50 years, and on the y-axis, this is the changes in coastal nitrogen inventory. So they have different units, so we're not comparing the values here. And each dot represents one coastal system. We can see it's a fairly good correlation between the two, showing that the accumulation of nitrogen in coastal system is the first order responses to the changes in river nitrogen loading. Okay, so since we're plotting on log scale, we do see some deviations, and because of the log scale, the deviation actually not trivial. So I wanted to look at what are the systems that actually deviates from the regression line. So I'm just identifying some example here: Yellow Sea, Baltic Sea, Hudson Bay, Norwegian Sea. Those are the ones above the regression line, meaning they're more sensitive to increases in river loading. So the one below the regression line, Bay of Bengal, crucial currents, meaning if you give a same amount of nitrogen added to those systems, they don't really accumulate that much, so they're less sensitive. And then I was wondering, what drives this pattern? What drives this different deviation from the regression line? And I started thinking about it, I realized those systems above the regression line seem to be the ones that are more retentive, that has a longer residence time. And those ones, crucial currents, those are more fast flowing system, not so retentive. So that sort of makes sense to me. If you have a system that is very retentive and you dump nitrogen there, and most of the nitrogen will be accumulating there. So I plotted the coastal residence time on top of it, and I did see some pattern. So those Yellow Sea, Baltic Sea, those have a residence time over a year, tend to be the one more sensitive to increases in river loading, versus those the ones that only a residence time of only a few weeks don't really accumulate that much with the same amount of river nitrogen loading. Okay, so that means coastal residence time really plays an important role driving the differential sensitivity of coastal nitrogen accumulation to the increasing nitrogen river loading. Okay, so how about the net primary production? And we also see a fairly good relationship, first order responses. Some of the deviating systems are Gulf of Thailand, for example, Norwegian Sea, East Bering Sea. Above the line, below the line, narrow currents, crucial currents again. But if we plot the residence time on top of it, I'm not really seeing a very clear pattern, although it seems to be the under-retentive system still be below the regression line. And similarly for benthic flux or oxidant demand, we also see this degradation of the correlation, and we can see the pattern is not really driven by coastal residence time anymore. So this suggests that there's other major driving factors that drive this differential sensitivity of ecosystem responses to changes in river nitrogen loading. So our hypothesis here, we're still investigating it, is that it has maybe to do something to do with the saturation state of the nitrogen in that system. Basically, if you have a system that is oversaturated with nitrogen, because not all systems are nitrogen limited, maybe limited by phosphorus and iron, and if you have the system that are oversaturated with nitrogen, adding any additional nitrogen from the rivers wouldn't make a difference. It will still accumulate, but it wouldn't trigger a major ecosystem responses. So that's our hypothesis. We're still investigating it. All right, so just some quick take-home messages. River nitrogen loading to the global coastal ocean has increased dramatically over the past half century. There's almost 30% increases just over the 50-year period, from 36 to 49 teragram nitrogen per year. And 35 teragram nitrogen has accumulated in global coastal waters. And eutrophication has led to elevated primer production and a basic oxygen demand in about 29 out of the 66 coastal systems that we examined. And eutrophication and coastal ecosystem sensitivity to increasing river nitrogen loading varies substantially across different systems. So we can see that coastal residence time plays a critical role in driving the sensitivity of coastal nitrogen accumulation to river nitrogen loading, but we see more factors contributing to the sensitivity of the ecosystem responses. All right, so I'll end there, 5 minutes left.
Okay, questions for Xiao?
Hi, I'm Matt Long from NCAR. I have two questions. One is how you're treating other constituents. Other constituents, P,
Oh,
FE.
yeah.
And the second question is, are you thinking at all about the role of estuaries and pre-processing material before it's delivered to the
So
ocean?
I've actually put it here. They didn't have time to go over it. Those are the challenges of scaling up from local to global, and at a quarter degree is very difficult to resolve coastal, the estuarine process. But I started to think about this, whether we can parameterize the coastal burial, or how much is being processed in coastal waters. Like Will Barrison asked, can you give me a number? If you can give me a number, different system, I can put that number in the model and it'll be simple. But do we have a number for every single system? We don't. So we need more observations currently. So you're asking about other treatment of atmospheric deposition.
No, other constituents in rivers.
Oh, yes, okay, sorry. So currently, we have varying phosphorus, varying nitrogen. So nitrogen comes from the land model. Phosphorus, we don't really have a clear understanding whether it's a train and whether it's following nitrogen, the dissolved nitrogen, or the particular nitrogen. So we're taking the nitrogen to phosphorus ratio from different pools from the global news, and then we convert from the DIN to changes in phosphorus. For other carbon and alkalinity, we are using constant values, and definitely we need, these numbers need to vary, but we need more data to drive the model.
You sort of try to get to that in the last. Anyway, wonderful talk. Everything you talked here is very relevant to how the coastal CO2 budget changes over the last century from maybe a CO2 source to a sink. Do you have any implication from your talk?
Right, so this is not about carbon, because for rivers, the river really a big contributor to carbon variability, so we're not really resolving that at this moment. But here, one of the questions I'm interested in is the given continental shelf a nitrogen source or sink? And it may be directly or indirectly related to the carbon source and sink. So we can see across different oceans, many of the systems are sinks, many of the systems are sources. And having the river nitrogen, the outgassing, just add one more uncertainties on top of it. So this is what I can get from the model for nitrogen.
Hi, Allison Santoro, UC Santa Barbara. Your schematic suggested the answer is yes, but are you explicitly representing nitrous oxide in the model? And if so, did you do any analysis of your output?
So that's a very important contributor to the climate. But basically, we just have this denitrification process as the one loss term. So it's based on Middleburg. So we don't really have that coming out of the ocean. But we consider it as a loss term as part of the denitrification process.
Samantha Sidlecki, University of Connecticut. I'm over here.
Yeah.
I was a nice talk. I'm curious about the residence time and age tracer part of the dye experiments. How did you calculate or define your residence time or
Right.
age
So
calculation?
what is unique about our definition of a coastal residence time is it's not confined within one coastal system. So you may have the water coming from one coastal system to the other, and we will carry this age while it's traveling along the coast, because that's important. You're carrying the coastal properties while you're aging. So what we do is we have this age tracer that is incrementing when it's on the shelf, and we're decrementing by 1 when it's out of the shore. But we're not resetting it to 0, different from the ventilation age tracer. So we're allowing this water meander across the coastal and open ocean. So they may go out and they're degrading and decrementing, and then come back and incrementing. So and we have to run the model for really long time scales in order to get this mean state of age. But this age tracer is subject to the diffusive advection, everything in the model. Yeah, you have a vertical gradient, but it's not changing with the vertical gradient. So as long as it's on the shelf, it's incrementing. It's a paper on the revision, should hopefully coming out soon. Yeah.
Okay, great. Well, let's
Okay.
thank Xiao one more time.
Yeah.